Now when we looked at the Carnot engine, if you recall the Carnot engine, it takes an amount of heat QH at a temperature TH, dumps an amount of heat QC to the cold reservoir and does an amount of work W. And surprisingly enough, when we analyze the Carnot engine, all the processes in the Carnot engine were reversible. What we found out was QH over TH is equal to QC over TC. So then we argued that this relation we can write down in this particular more simplified form, not a more simplified form, but just simply write it down in this way. And as it turns out, since when we looked at the processes for the Carnot engine, there were two adiabatic processes and there were two isothermal processes. So let's just do it properly. And heat was taken in this part, heat was taken in this part, and no heat transfer was allowed in the adiabatic processes, which were this. And therefore it follows that if for the whole cycle, if we write down an integral d cut q over t, and if we evaluated this integral for the whole cyclic process in this way, then we would simply come up with QH/TH minus QC/TC, and that would be 0. So clearly it appears that this equation can be written down in this particular form, where now I have introduced ds is equal to d cut q by t. The implication of this equation is that this quantity s is now a state function. Since I have taken down the system, taken the whole system, the Carnot engine, in a cycle, and therefore I find that there is no change in the quantity s. And this is what we call entropy. And I find out that there is no change in the entropy because the system comes back to its original. Therefore, I conclude to this original starting thermodynamic state, and therefore I conclude that this is a state function. And it does not, therefore, it does not depend on path. But you see, in the whole argument, whatever we did, this integral 0 is true for reversible processes. In Carnot engine, all the processes are reversible, and therefore it's kind of an idealized engine, and so this integral is valid. Now, my natural question is, if I remove this restriction that if my processes are not reversible, then what happens? So, what happens to this inequality? And that is what we want to find out. So, imagine that I have a system that works in a cycle. So, we'll call this cycles P, and this is my system. And this system receives an amount of heat Q1 at temperature T1. It receives amount of heat Q2 at temperature T2, and then again let's say it does it with Q3. It receives an amount of heat Q3 at temperature T3, and so on and so forth. Now what I can do is, for further analysis, I can direct all this heat to a Carnot engine, which extracts some amount of heat from the heat reservoir at a temperature T0. So therefore I operate a Carnot engine which extracts Q2 0 amount of heat. Here I operate a Carnot engine which extracts Q1 0 amount of heat, and here I operate a Carnot engine which extracts Q3 0 amount of heat, does some work, so on and so forth. Correct? So these are all my Carnot engines, and there is no loss in generality in writing it down in this particular way. Now I want to look at the energy conservation. It obviously means that Q10 is equal to W1 plus Q1. and for the Carnot engine C1, and similarly for the Carnot engine C2. So the general relation would be Qy0 is Wi0 plus Qy, right? The work done by the system is simply minus, so if I want to write down the energy conservation for the system, then the work done by the system in the whole cycle plus Qy must be 0, and therefore W is sum over Qy, right? What is the total amount of heat taken from the reservoir? The total amount of heat that is taken from the reservoir is sum over Qy0. Now remember, for all of these Carnot cycles, I can again write down the relations. Q10 over T1 over T0 is Q1 over T1. And again for the second one also I can write down, sorry, this has to be T0 is Q2 over T2, because it is taking a heat Q10, Q20, Q30 and so on from the temperature T0 from the hot reservoir, and it is dumping heat Q1, Q2, Q3 at temperatures T1, T2, T3 respectively. So the general relation becomes Qi0 over T0 is equal to Qi over Ti. I'm going to use this relation. So this means that this I can write down T0 sum over Qi0, sum over Qi over Ti. Right? So what is the total work done? The total work done is minus W plus, we will put a subscript, because work is the energy which is flowing out of the system, therefore in our convention it should be minus Wi. So minus W is minus sum over Qy, and then we will write down this as minus sum over Qy0 plus sum over Qy. This follows from here, where I can recast this equation as Wi is Qi0 minus Qy. So once I have this relation, therefore it follows that this is sum over Qi0, which is minus Qt total. Now what one can do is one can think of this as a whole kind of a system which is doing an work Wt, right? If that is the case, then it follows that if Qt0 is positive, then Wt is negative. What does this mean? This means I have this box, I have the system inside it where it is receiving all this amount of heat, but as the whole system, what it does, it takes Qt0 amount of heat, enters this box, this taken system plus Carnot engines taken together, because it's positive, and it is doing an amount of work Wt. But this, what about the other one? Okay, let's just look at the other one where Qt0 is negative, that means Wt0 is positive. Here of course what happens is the arrows get reversed, so Wt and then Qt. Now the problem with the first thing is that if you allow this, then you violate Kelvin's statement. Why? How do you violate Kelvin's statement? Well, because you are extracting some amount of heat, you are extracting it, heat, and then converting it to work. Completely to work. In contrast, this does not violate, right? This because there is no thermodynamic principle that says, oh, I cannot convert work into heat. Therefore, it follows that Qt0 must be less than 0. But what is Qt0? Qt0 is sum over Qi0, which is sum over T0 Qi over Ti. This implies that Qi sum over I must be less than equal to 0. Well, in this particular case, it must be just less than 0, but we'll combine them, right? Since T0 is positive quantity. Once you have this relation, you can imagine that all these heats now are infinitesimal heats. Therefore, I can write it down in the more general case where I have infinitesimal, so I have the system and the heat transfers are infinitesimal. That happens at different temperatures, so I can generalize this as less than 0. So whenever the processes in the system involved are not reversible processes, the most general, so in the reversible case we saw that d cut q over t is equal to 0, reversible, and for irreversible processes this integral must be less than 0. If I want to convert this, not convert this but combine these two, it follows that general for any arbitrary process I must have d cut q is less than equal to 0. So this quantity is called, or not this quantity but this inequality is called Clausius inequality. And it's very, very important in thermodynamics. So Clausius inequality tells me that Clausius inequality tells me that d cut q by t must be less than 0. Right? Now, one thing I want to make clear over here that, see, in thermodynamics, whenever we're doing the formulations of thermodynamics, we always say that ds, d cut q, d cut w. What does this mean? This means that there are always infinitesimal changes or quantities we are talking about, and this essentially means that if I have the thermodynamic state and then I take a thermodynamic state to a state which is very, very close to A, an infinitesimal change in its macroscopic parameters. How much change in infinitesimal change in, or how much amount of heat is the system taken? Does the system take or give off? That is d cut q. How much amount of work does it do? That is your d cut w, so on and so forth. Right? Now imagine that you take the thermodynamic system from the state A to a state B, right? And you do it via a reversible process. You bring it back from B to A via an irreversible process. But then you know that for the whole cycle from A to B and B to A, so you are going like this and coming back like this, and then for the whole cycle d cut q by t must be less than equal to 0. Now let us write it down in the more explicit form. So I have d cut q reversible over t plus b to a d cut q over t must be less than equal to 0, right? But I know what this quantity is. For a reversible process, I can define this as SB minus SA, right? Plus B to A d cut q over t is less than equal to 0. So this follows, thus SB minus SA is greater than equal to if I want to write down this relation in a differential form, I will write down ds is greater than d cut q by t. Remember that this d cut q that you have written down is for irreversible processes. So let's just and the relation d cut q over t is equal to ds is valid only when you are considering a reversible process. So this entropy, what does this mean? Let's be more explicit about this. This entropy or any other thermodynamic parameter, if I have a reversible process between A and B, then the entropy is defined for all the thermodynamic state points which lie on this curve, if this is reversible. In contrast, if it's an irreversible process, this essentially means that it is only defined at A and B. Otherwise, it's not. So, therefore, I have this particular relation ds which is greater than equal to d cut q by t. Now, imagine that you have a number of systems which are isolated, or you can also think about adiabatic system. So these systems are isolated, which means there is no universe, no path, nothing around it, and therefore when you bring them together, so they are adiabatically insulated, then essentially this means that there is no heat exchange, and if there is no heat exchange, this means that ds must be greater than equal to 0. So this is a very, very important consequence. It tells you that when the systems come to a joint equilibrium, they kind of go to the maximum entropy state. Of course, this also has to mean that the system is isolated system, right? So your joint equilibrium, or the final thermodynamic state, is the one which has the maximum entropy. So any spontaneous fluctuation why do we talk about any spontaneous fluctuations? Because your system, which is made up of smaller subsystem, is insulated from the outer world. So therefore there is no heat, no energy which flows out. So anything that can happen inside is a spontaneous change. So any spontaneous fluctuations in this system must give you ds greater than 0. So which means that if they want to come to a joint equilibrium, then they have to maximize their entropy, right? So I know that ds is d cut q by t. So in principle, therefore it follows that d cut q by ts, and this is true for all reversible processes or quasi-static processes which are necessarily reversible. Okay, so therefore I can rewrite down my first law as dds is equal to du minus sum over fi dxi. If you have forgotten what this means, the fi is my generalized forces which are intensive in nature, and these are my generalized coordinates which are extensive in nature. In addition to that, now I have the information that the quantity S is a state function, the entropy is a state function, it does not depend on path. Similarly, U is also a state function. We have seen that when we wrote down the first law, that is to say that this also does not depend on the path. So whenever you see, when I write down path, you are familiar with trajectories in mechanics where you plot x and t and you said, oh, this is the path the particle takes. But here, this is the path that is referred, that is essentially the path which is taken by the system in the macroscopic coordinate plane. And we have seen such examples where we had, if we have a pressure volume for a hydrostatic system, we have seen that this can be the path, this can be a path, this can be a path, so on and so forth. So all of this refers to the path that we are talking about, and both S and internal energy does not depend on the path. If it's a reversible process, it only depends on the endpoints, right? So for a hydrostatic system, we will just write it down quickly. For a hydrostatic system, which is essentially a fluid, my first law equation is du plus pdv minus mu dm. Now, in thermodynamics, u, v and n, or u as a function of s, v, n, these are called, let's just highlight this a little bit and write it down as fundamental relations of first kind. And these are the most powerful relations that you can have. For example, if you know either S as a function of UVN or U as a function of SVN, you can invert either of this, and then essentially you can calculate the heat taken, the change in entropy, the work done, all of this, provided you know this. The second one is, of course, what we call the equation of state. Now the equation of state is, if I write down like this way, du minus fi dxi, then you clearly see that del s del u, the derivative holding all the coordinates fixed, must be equal to 1 by t. Similarly, del s del xi, sorry, this is del xi, holding u and xj with j not equal to xi must be minus fi over t. This equation is called an equation of state, and this relation is going to give you u as a function of t. So clearly I have two approaches. Given this relation, I have nothing to worry about. For any thermodynamic processes that is given to me, I can evaluate this. The second route is this one, where you are rather not given the fundamental relation. So these are called fundamental relations of second kind. If you are given the equation of state, then you necessarily can reconstruct back the entropy, the fundamental relation. That is always possible. But you have to know all the equations of state. So if you write down for the hydrostatic system, which is for a fluid, TdS is du plus pdv minus mu dn. In this particular case, you have to know u as a function of t, p as a function of v and n and t, and also mu. If you know all of this, then you can reconstruct back this. How? Well, that is very easy, because you know that del s del u is equal to 1 by t. Xi are fixed. And similarly, you can use these relations, these two derivatives, you can integrate out to write down this as. So in one case, let's be explicit here, since I have already written down the first law. So del s del v is u constant and n constant is p by t, and del s del n u constant and v constant is minus mu by t. So you can replace this over here and integrate out to determine s as a function of u, v and n. Right? So we will come back to all of this a little later, but I want to discuss something. So we have seen that ds must be greater than or equal to d cut q by t for any general process. Right? This means that if I have a system which is adiabatically strained, which means there are no possibilities of heat exchanges, and it comprises of subsystems which are in equilibrium themselves and are brought together, then since there is no heat exchange possible, any spontaneous change within itself can only lead to a maximization of the entropy. So we say that the maximization of entropy leads to a thermodynamic equilibrium state, correct? But now I know that the entropy is a function of u and xi. This is my fundamental relation of type 1. So for a hydrostatic system, I know that we have seen that S is a function of u, v and n. See, the forces are not appearing here, the Fi's are not appearing, it's always the generalized coordinates, right? So it follows, let's take a system where I have fixed the xi's and I am only interested in looking at in this plane. Now let's draw a line over here. All the points on this line corresponds to the equilibrium states, and all the points below this line essentially comprises of your non-equilibrium states. So these are your non-equilibrium states. Can you find out why these are your non-equilibrium states? And all the points on this red line or red curve is essentially the equation S as a function of u, where xi's are held fixed, right? Now imagine that I fix the entropy of the system. If I fix the entropy of the system, I have also fixed the coordinates of the system, then you see there are several thermodynamic states are possible, correct? But none of these are equilibrium state. The equilibrium state always corresponds to the minimum energy, the one which has the minimum energy of all the states. In other words, essentially this means that your maximization of the entropy is equivalent to minimization of internal energy. Of course, the point here is that I have cheated a little bit. You will see why. Now, this is only possible, you see, when S is a monotonically increasing function of u. So when S of u is a monotonically increasing function. And this is where I have cheated, because I have drawn a monotonically increasing function, right? Clearly, if you had this like this or in some other way, then this would not have been possible. And the property of the monotonically increasing function would mean that del S del U must be greater than 0. See, xi's are held fixed, I have also held fixed. But this essentially means that the temperature must be positive. So positivity of the temperature implies maximization of S and minimization of U are identical, the same thing that you are doing, right? This holds because your temperature is positive. Your temperature is positive because Kelvin's statement of second law prevents a negative temperature, right? So everything is kind of falling in place and there is nothing. So this more or less now we are done with thermodynamics, or rather we have learned of what are the guiding principles in thermodynamics. Now I want to apply this, right? So for that we have to look at processes, and as we said before that S as a function of UVN for a hydrostatic system, or equivalently S as a function of U of Xi. These are, or U as a function of SVN for a hydrostatic system, U as a function of Xi are the fundamental relations. So if I know this, I know everything. And since you see, when we formulated the thermodynamical principles, we are always writing down differential change, and therefore partial calculus would give us all the answers we want to look at. So any thermodynamic process you can imagine must obey the first law and the second law, right? Which in sum therefore should be du minus sum over Fi dxi, right? We will take the example of the hydrostatic system where S is a function of UVN or U as a function of SVN. Now let's look at processes. So how can you take the thermodynamic system from A to B? There are several ways. You can keep pressure constant, you can keep volume constant, you can keep temperature constant. Usually particle number is always held constant, so we will not talk about n explicitly unless we want to. And you can also keep entropy constant. Right? This is what is known as isocodic process. This is known as it's the other way around. This has to be an isobaric process. This has to be an isocodic process. And this has to be this is what is called an isothermal process. This is isentropic process. You have to realize that depending on the thermodynamic coordinates that you choose, these processes look different. So if I, for example, take the PV diagram, let's use a different color now. So if I use a PV diagram now, an isobaric process is where you take the system from A to B, right, where your pressure is held constant. And isocodic process would be this one where you take from B to C, where your volume is constant. Now clearly, how does an isothermal process or an isentropic process look? For an isentropic process, for this you have to know the type of system you're looking at. If I look at an ideal gas, then I know that PV is NkBT. So therefore, I know that if it's an isothermal process, then pressure must go as 1 by V. If it is an isentropic process where the entropy is constant, which means it's an adiabatic process, no heat exchange, that would also mean that PV to the power gamma is equal to constant. So these are the kind of curves you expect as you take it from in the PV diagram, and we have seen the example of that in the Carnot engine. One of them was like this, the other one was slightly steeper, right? So this is isothermal and this is adiabatic. So you take the system from B and C, right? The work done for this particular system is PDV. In general is Fi dxi, sum over I. If you have one force, then it is just F1. Sorry, if you have just one thermodynamic coordinate, for example here I have only one extensive coordinate for the hydrostatic system, which is the volume, because n is typically held fixed here, then this is the case, is the work done. And therefore the total work done would be integral d cut w, which is integration p dv, right? So these are the nitty-gritty details, calculational details of how you calculate the work done, the heat exchanged, so on and so forth in this system. Given S as a function of UVN, now typically whenever we will give illustrations, we will only concern ourselves with hydrostatic system, then change in entropy is ds. It's a state function. If it is taken from A to B, then I know that this is SA minus, sorry, it's going to be SB minus SA. The change in entropy, let's say, is going to be delta S is going to be SB minus SA. If you know this relation, then of course you know U as a function of SVN, then the change in internal energy would be UB minus UA, provided you know these relations, right? If I have an isobaric process, I can ask, what is the change in entropy? As the system goes from A to B, I am not constraining myself to an ideal gas for any arbitrary system. The answer is very simple, and herein where partial calculus help us. Entropy is a state function. Therefore, here you see that I have an isobaric process. In the isobaric process, the pressure is held constant. Therefore, the temperature and the volume can change for a hydrostatic system. So what I am going to do is I am going to write down S, take S as a function of P and T. I will not worry about volume. You have to understand also that not all the three equations of states are independent, because you can eliminate between them. Only two of them are independent quantities, and that is tied down very closely, and that is because of your Gibbs to Hem relation, but we'll come to that. So if I write down S as function of P and T, then ds by rule of partial derivative is temperature constant dP plus del S del T pressure constant dt. But look, it's an isobaric process and I have held pressure constant, therefore dP must be 0. So it follows ds is Cp dt, Cp by T dt, where Cp is T del S del T, pressure constant, is the specific heat at constant pressure, right? If you are looking at an isochoric process, You can do the same thing if I ask you what is the change in the internal energy, right? If you're looking for an isocodic process, then you will write down this as V comma T, and you will see that ds is CVT dt, and the heat taken out is just TdS, which is just CVDT. In this case, it is CPDT, right? For an isothermal process, your temperature is held constant. So you can take either as a function of P and T or V and T. You can also take here as a function of V and T. But here you have to note that if you, in the isobaric process, if you take S as a function of V and T, then your ds is del S del V, temperature constant, dV plus del S del T, volume constant, dt. This is equal to del S del V, temperature constant, dV plus Cp by T dt. Please note that your dV is non-zero because your pressure is held constant but not the volume, and you have to somehow manipulate this derivative. We will do it later on once we have introduced Maxwell's relations and so on and so forth. Now for the isothermal process, coming back to it, I can either have S as a function of P and T or S as a function of V and T, in which case, since dt is going to be 0, a priori I know it is going to be del S del P, temperature constant, dP, del S del V, volume constant. ds is going to be del S del V, temperature constant, dV. Depends on what information is given to you. So if you're asked to calculate the change in entropy, given that your pressure doubles, then you're going to use this first relation, S as a function of P and T, and if it is for you're given the information that your volume doubles or volume halves in the isothermal process, what is the change in entropy or how much heat is taken, then you precisely do it the second way. You take the second relation. So you essentially get the general idea of how to deal with thermodynamic processes and thermodynamic systems. Again, let us just very quickly summarize that for a given thermodynamic system, I have a set of intensive variables and a set of extensive variables. Xi, Fi. First law is delta Q, or we will write it down in the differential form. d cut Q is du minus d cut W. d cut W is Fi dxi, so that d cut Q is equal to du minus Fi dxi. If you have two coordinates, two terms is going to come, three coordinates, three terms is going to come, so on and so forth, and then enters the second law that tells you that ds must be greater than equal to d cut Q by T. If it's a reversible process, then you have ds is d cut Q by T, and therefore you have TdS is equal to du minus sum over Fi dxi. Once you have written down this differential form of the first law, you immediately say that del S del U xi's, all the coordinates held constant, must be equal to 1 by T, and del S del xi U and xj, which is not equal to xi, which is not equal to xi held constant, would be minus Fi over T, right? And these are your equation of states. If you are given S as a function of u and xi, then you can write down ds as del s del u xi held constant du plus del s del xi u and xj not equal to xi held constant dxi, right? And then you can immediately relate it with these derivatives. You can of course have the other way around, where you have u as a function of x and xi, in which case du is del u del s, all the coordinates are held constant, ds plus del u del s, not again an s but rather the coordinates xi with the entropy and xj not equal to xi held constant dxi. And then you can immediately compare, once again you can immediately compare it with the first law and see that del u del s xi held constant must be t, and del u del xi entropy xj not equal to xi must be equal to fi over t. So essentially, given these two relations, you can derive the equation of state that relates the fundamental, that relates the forces with the coordinates, right? For an ideal gas, this would be like PV equal to NKBT and U is equal to 3/2 NKBT. Okay, so now we have mostly covered this part.